by using the capital asset pricing model regression, we want to say something about the variance, or the relationship between Sony stock and the market, and we want to say something about the risk, or the riskiness of the Sony stock, and whether or not it outperforms the market. But before we get to that, we do the regression, where we have the percentage. Oh, let's see, just move some chords here. Like the Sony stock returns on the intercept, the alpha, because often people use the Greek letter alpha for the intercept, plus the slope, which is called the beta, times the percentage change of the market, plus an error term. Okay, and we need to know, this is the Sony, this is the market, and what we want to check if a linear model is correct. And apart from two outliers here, one hugely positive and one hugely negative, then this relationship looks linear, which means that we can't really detect any non-linearity in this scatter plot. And if we plot the residuals versus the market change, then we get the same result. And what we notice is that we have these outliers. Okay, so, and these occurred when the market moved up around 8%, and for 1 month the Sony stock lost almost 40%, and for 1 month the Sony stock gained around over 40% more than the market, okay, or the expected value of the market, okay, which means that it looks linear, and we can't really detect any change in variance apart from these two outliers, that is. So we can't really say that there are any patterns in the residuals. So no patterns. So there are no patterns in the residuals. So this is check and this is check. Okay, so that means we can go on, but since this is a time series, it means that we should also look for dependence over time. And what we do is that you plot the residuals on the time, and you look for patterns. And what you do is that you can check for dependency over time, like trend, which should be removed if you have correct model specification, but you should perform the Durbin-Watson test. Of autocorrelation. Okay, and here we have no problem, and you should check that the residuals are normally distributed. Okay, so let's see. Check for normality. Okay, because if the residuals are not normally distributed, then you can't use the standard error or standard deviation of the residuals to create this prediction band, okay, prediction interval. So if you do the regression, then what you want to look at is the R squared, and preferably the adjusted R squared, which takes into account how many variables you put into the regression. And you see that you can explain 31.7% of the variance or the variation in Sony change. This is the y variable, and so by using the market, you can explain about 1/3 of the variation in the Sony stock. And what you have is this B1 coefficient that would be the beta of Sony, that would be 1.27, and with a standard error of 0.13, which means that the Sony stock is significantly different from zero. Okay, and the constant B naught, this is the alpha, is negative 0.53, so it's negative 0.5 percentage points, but the t-value is low, so you can't say that it's different from zero. And how do you interpret the B naught, the alpha? Well, the B naught, it's negative 0.52, right? Or was it 532? 532 it should be. And what this represents is that on average, Sony stock underperforms the market by 0.532 percentage points. Which means that every single month you expect the Sony stock to return half a percentage point less than the market itself. Okay, and if you go by this model, okay. And how do you interpret the B1, the beta? So B1 equals 1.27 something 78. Okay, so this is given a 1% market return. You would expect Sony stock to increase by 1.278%. Okay, which means that Sony stock is more volatile than the market. Okay, and if you had a -1 market return, a -1% market return, you would expect Sony stock to decrease by 1.27%. Okay, is the estimate B1 statistically significant at the 1% level? Okay, let's see. So the t value is 9.69, and the p value, is very close to 0. So yes, the p value is almost 0. So yes. Okay. Let's see. Is the two-sided test H0 beta 1 equals 0? Okay, so the slope equals 0, and the alternative hypothesis H1 equals beta 1. The slope is different from 0. Very interesting. Well, if the slope had been not different from 0, then the stock would not move at all with the market. Okay, and you would actually expect stocks to have some covariation with the market. So we would not use the CAPM model to test stocks on this, maybe other kinds of assets, but so this is not really interesting. No, because because you would expect stocks to move with the market, okay? But this is a slightly more interesting test. It's testing whether or not the slope, the beta, which says something about the variability of the stock, whether or not it's the stock is varying less or more than the market as the market moves. Okay, so because if you have let's see, if beta greater than 1, then you say that you have like an aggressive stock, okay? And if beta less than 1, then you have like a passive stock, okay? Because your stock is not moving with the market as much, right? So this hypothesis is actually quite interesting because it also gives you how many futures you have to buy in order to hedge your position. So it's actually quite interesting for the optimal hedge ratio. Okay, but you're not going into that in this course. Okay, but what is the p-value of the hypothesis test? H0 is beta 1 less than 1, and the alternative hypothesis is beta 1. The slope is greater than 1, which means that the stock is moving more than the general market. So so this is Sony stock moves less than the market, and this is Sony stock moves more than the market. Okay, so what we do then is to check the T statistic. Okay, and what we do is that we have the slope. We have the slope 2.78, and then we subtract the cutoff value. Okay, you remember the cutoff value. So, and we are testing versus 1 and dividing by the standard error of the slope, and the standard error was here. Okay, so we have used the coefficient, okay, and we have used the standard error 0.1319, which is 0.1319, which gives us 2.11, if I remember correctly, and is this significant, well, what you can do is that you find the probability of getting something more extreme than this, and then you use the t-distribution, which looks like the normal distribution, only it has like fatter tails, and then you find the, well, if you center it at 0, then you find the t statistic 2.11, and by table you find the probability of getting like a t-value greater than 2.11, right? And you can find this in a table where you look for the degrees of freedom, and you have a degree of freedom of, let's see, number of observations is 204. 204 minus the number of parameters in your model, which is 2, which gives you a degree of freedom of 202. Okay, so now you have the t statistic, now you have the degrees of freedom, and I can show you how to find the let's see here. I've done this. You just type in, let's see here. You just type in instead, you type in display just to get the result printed to screen, and then you use the function t-tail, okay, t-tail, t-distribution tail with degrees of freedom 202 and your t-value of 2.11, and then you get the result 0.018, which is 1.8%. So by doing this instead, you can find the p-value. This is the p-value, the probability of getting a more extreme t-value than 2.11 with 202 degrees of freedom. So this means that the p-value is around 1.8%, and if we are using a 5% significance level, then we reject H naught of beta 1 less than or equal to 1 at the 5% level. Okay, which means that we jump to the alternative hypothesis that the slope is indeed greater than 1. And for our next video, we're going to talk about expanding the regression model.